Okay, we can continue from where we left. So let's look at example number 7. So if you let E1, which is a vector, to be 1, 0, 0, E2, which is also a vector, which is equal to 0, 1, 0, and then E3, which is also a vector, which is equal to 0, 0, 1. These are what we call the standard vectors. We'll see it in our next section. If these are our standard vectors, and also if we have y1 equals to 1, -1, y2 equals to 0 and 1, and then y3 equals to 1 and 1. Now, if the transformation T is from R3 all the way to R2, is a linear transformation. It's a linear transformation such that T EI is equals to YI for I equals to 1, 2, and 3. Then find the transformation of 2, 3, and 4. Find the transformation of 2, 3, and 4. So if these are the E1, E2, E3, and then we are told that the transformation of E is equal to Y I. The transformation of E equals to Y I, or I equals to 1, 2. Then find the transformation of 2, 3, and 4. So what is our solution here? So let's look at this. So we can express this vector here. It's a linear transformation of E1, E2, and E3. So we can say, we can express vector 2, 3, and 4 as a linear combination of E1, E2, and E3. E1, E2, and E3. So how do we express this as a linear combination? So this is actually similar to, so it is 2, 3, and 4 is equals to 2, 1, 0, 0, plus 3, 0, 1, 0, plus 4, 0, 0, 1, plus 4, 0, 0. So, and this is similar to 2E1 plus 3E2 plus 4E3 plus 4E3. So that is now expressed as a linear combination. As a linear combination. Now, when we introduce now the transformation, now when you put now the transformation, Then T now of 2, 3, and 4 is equals to now T of 2E1 plus 3E2 plus 4E3 plus 4E3. So when you introduce now the transformation, yeah, and also use it. And this now is equals to, so this one is now equals to, now distribute the transformation there. So it is now equals to TE1 plus 3TE2, and then plus 4TE3 plus 4TE. And we have said that TE and EI is, let's say, 1, 2, and 3. So from here, such that TEI equals to YI. So therefore, then this TE1 will now be similar to Y1. So then the transformation of 2, 3, and 4 is now equals to 2. This is now Y1 plus 3Y2, and then plus 4Y3 plus 4Y3 plus 4Y3, which is now equals to, so we have our Y1, so it is now equals to 2. Y1 is 1, -1, plus 3. Y2 is 0, 1, plus 4. Y3 is 1, 1. So finally, then you open that bracket. So therefore, our T 2, 3, and 4 will now be equals to 6, 5. Will now be equals to 6, 5. Any questions? Okay, now let's come to the next section, which is section 1.9. Section 1.9. 1.9. This is the standard matrix of a linear transformation. The standard matrix of a linear transformation. So we will start from the number 1, the standard basis vectors and standard matrix. Standard matrix. Start from 1.1. What is the standard basis vectors? Standard basis vectors. So the standard basis vectors is, so the following n vectors in Rn are standard basis vectors for Rn. For Rn. So E1 is just similar to what we just wrote, 1, and then the others are zeros up to n. E2 is just the same as what we wrote, 0, then the second one is 1, and then all are zeros up to n. And then if you continue like that, En is equals to all these are zeros up to the last one, which is n is 1. The last one, which is n is 1. So those are the standard vectors. The standard vectors. So these are exactly the columns of identity matrix. So these are exactly the columns of identity matrix. So we can say they are exactly columns of the identity matrix, which you can say that identity matrix S I N S I N. So we can express this as a linear combination. So we can say every vector X in Rn can be expressible as a linear combination of E1 all the way to En if X equals to X1 all the way to Xn. Then our X can be written as In and then the vectors X. So you remember when you multiply an identity matrix by a matrix, then you still get the same identity matrix, right? So if you have the vector X, and then now you multiply by the identity matrix, then it is giving us a linear combination of those X, which we can write this as E1 all the way up to En, and then multiplied by X1 all the way to Xn here, which can still be the same as X1 E1 plus X2 E2 plus Xn En. And these X1, X2, Xn are now the weights. So those are now the weights. So the weights in the above linear combination are exactly the entries of X. Exactly the entries. Entries of X. Okay, now let's come to the next theorem, theorem 1.2. If we let the transformation from Rn to Rm be a linear combination, and define the M by N matrix A to be equals to transformation of E1, transformation of E2, all the way to transformation of En. Then Tx equals to Ax for any x element of R n for any x. element. So if you have the transformation from Rn, Rm, so linear combination can be defined as A equals to the transformation of E1 E, whereby T of X is the same as A of X. E of T of X is the same as A of X. Then if we prove this, then what we can do is we can let's prove this. So we can let X to be equals to X1 all the way to Xn. All these are elements of X. Be vectors in Rn. Then T of X will now be equals to T of X1 E1 plus X2 E2 plus Xn En, which is similar to taking this transformation inside, which is similar to X1 T E1 plus X2 T E2 plus Xn T En. So it's similar to taking that transformation inside. Therefore, this is now the same as putting this one in matrix form, which is now the same as T E1, T E2, T En, and then you multiply by what? X1, X2, Xn, which is the same as A X, which is similar to okay, let's look at example number 1. Let's look at the first example. Example number 1. Let's the transformation from R3 to R2 be a linear transformation such that TE1 equals to 1, -2, TE2 equals to -1, 0, and then TE3 equals to 3 and 3. Now write out the standard matrix of T, and then compute the image of X is equals to 1, 2, and 3 under T. Under T. So there's that transformation. There's that transformation. So solution. So let's start from the first one. Let's now write the standard matrix of this. So from the theorem that we just had, the standard matrix of T. So the standard matrix. Yeah. Actually, this is actually having a square bracket. It is not a parenthesis. So if you write in this form, if you're writing, let's say you're writing T, E, let's say E1, you can write in this form 1, -2, or you can write in the form 1 and -2. So you can actually write in that form. Okay, now the standard matrix, just from here, to get now the standard matrix here, to get A, then the standard matrix of T is the same as A, which is equals to T E1, T E2, and then T E3. So that is our standard matrix, which is now the same as 1, -2, -1, 0, and 3, 3. That is our standard matrix. This is our standard. Now let's now solve, or let's now compute the image of X. So the image of X, if we still remember, the image of T, we said is the same as T of X, which is equals to AX, which is equals to AX. So therefore, our T of X, which is the same as AX, is now equals to this matrix here, 1, -1, 3, -2, 0, and 3. And then we multiply by our X there, which is 1, 2, 3. 1, 2, and 3. So our T of X is T of X. Now A of X. And what you get here is, so you take the first, the row operation, like multiply by that. Some of you are not doing a good job in your exam. So when you're multiplying the matrix, then you take this row and that one. So this is similar to 1 multiplied by 1 plus -1 multiplied by 2 plus 3 multiplied by 3. To come to the next one is -2 multiplied by 1 plus 0 multiplied by 2 plus 3 multiplied by 3. And then you now add. So what you should get here is 8, 7. What you should get is 8. So that is what you should get. So that is the end of the standard basic vector and the standard matrix. Now let's come to the next section, which is number 2, which is the onto and one-to-one linear transformation. onto and one-to-one linear transformations. So anyways, you have done onto and onto, right? And then you've done most of the mathematics. So let's see what is this onto and one-to-one when it comes to linear transformation. So if we have, let's say this is Rn, and this one is Rm, and we are transforming from Rm. This is the transformation there. Now, when we say onto, then what do you mean? So let's look at 2.1 definition. A transformation T from Rn to Rm is onto if for each B, which is in Rm, for each B, which is here in Rm, then there is at least one vector X, which is in Rn. There at least one vector X in Rn, such that the transformation of X equals to, such that the transformation of X equals to B. And this is actually the same as, which you can name this one as image of T to be equals to Rm. So every element in this has an image or has a vector in this as at least an element in Rm. So it is mapping from here up to here. So they're so the image of T is actually equals to Rm. So the elements that here are mapping. So that be here. So it is setting an element in this. So that is onto. So that is onto. Now, let's look at theorem 2.2. Let's A be the standard matrix of a linear transformation T from Rn all the way to Rm. Then T is onto if and only if every row of A has a pivot position. Now, since Rm or M's are the rows, Rm and rows. So for onto, then when you reduce the matrix A, then for that matrix or for that matrix onto, then each row should be having the pivot position. Each row should be having a pivot position. We can prove this. So let's prove this one. Let's prove this. So if we write A to be equals to the vectors A1 all the way to AN here. So if those are the column vectors of A1, A2, A3, up to AN, where these A1s, these are actually vectors, all the way to AN are elements of, let's say, Rm. If these are elements of Rm, these are elements of Rm. Then the image of T is the same as the transformation of X, where X is equals to X1 all the way to Xn. And these are elements of Rn. These are elements of Rn. Then, since we said the transformation of X is the same as AX, then this is actually the same as AX, where our X is equals to X1 all the way to Xn, and these are elements of Rn, elements of Rn. And this is equals to the linear combination now, which is X1, A1, plus X2, A2, plus Xn, A. Where X1 all the way to Xn are elements now of real numbers. Elements of real numbers. So if you remember, the image is the same as the transformation of X, T of X, and you say T of X is equals to A of X. And this A of X is a linear combination of that. Then this is the same as the span of A1 up to what? AN. This is the span of A1. So image of T is equal to this. This is equal to this. This is equal to this. And this is equal to the span of that. So then we can say the range of T is the subspace of Rm spanned by A1 all the way up to A. And so our T is onto if and only if the columns of A span Rm, also every row of A has pivot positions. Every row of A has pivot positions. So if every row of A has a pivot position, then it means there is no free variables. There are no free variables. So each of the rows there should have a pivot. If it is not having a pivot position, then it is not on. Okay, now let's look at an example on this. So we say example number 2. Example number 2. If we let the transformation from R3 to R2 be the linear transformation defined by T of x1, T of x1, x2, x3, which is equals to x1 minus x2 plus x3, x1 plus x2 plus x3 for x1, x2, x3 elements of R3 is T onto, is T onto. So the transformation, yeah. T onto. So how can we solve this? How can we solve this? So what you can do is we can do the solution. So we can actually, if you remember by definition, so we said T of E1 are the same as 0 or 1, 0, 0. So where this is 1, and all these are 0. T of E2 is 0, 1, 0. That means x2 is 1. T of E3, that is x3 is 1. So now T of E1 is where x1 is 1 and the others are zeros. So in this case, if we now substitute the values of x1 here to be 1s and the others are zeros, then what do we get? So the first one is here is 1, the others are zeros. So it is 1 and what? And 1. Since the others are zeros. T of E2, all the others are zeros and x2 is 1. So this is 0, x2 here is 1, so it will be negative 1. This is 0, this is 1. And then T of E3, all the others are zeros and E3 is 1. So this is 1, and then this is 1. That is 1. That's 1. So now when we put this one in matrix form, so A will now be equals to TE1, TE2, TE3, which will now be equals to 1, 1, negative 1, 1, and then 1, 1 there. Now, when we now reduce this matrix, so when we reduce this, so to get the new R2, then R2 minus R1, what we get is 1, negative 1, 1, 0, 2, and then 0 here. 0, 2, and then 0. So what can we see there? We have pivot positions in each of the rows. So this row has a pivot position here. This one has a pivot position there. So we can say every row of A has a pivot position. So T is onto. T is onto. Any question after that? Any question? Okay, now let's come to the next one. which is 1 to 1. 1 to 1. So let's look at definition 2.3. Definition. A transformation T from Rn all the way to Rm is 1 to 1. We can actually write like that, 1 to 1, 1 to 1. If for each vector B in Rm, there is at most one vector X in Rn such that T of X equals to B, and we can name this one, namely T of U equals to T of V, where this U is equals to, where U is equals to. So when you say it's onto, then we take at least for onto, say for 1 to 1 is at most one vector, except that T of X equals to U, where T of U equals to B equals to U equals to. Okay, let's look at the theorem 2.4 theorem. We let A be the standard matrix of a linear transformation from T of Rn all the way to Rm. Then T is 1 to 1 if and only if A of X equals to 0 has trivial solutions. As trivial solution. Okay. So as trivial. For this one to be onto, then this should have trivial solutions. Basically, we use this, then all the columns should have trivial solutions. The other one was all the rows. This one, all the columns should have it. One to one. For this to be 1 to 1. Okay, we still have some time. Let's briefly prove these. So we can prove. So for this one is if and only if, so it has 2 directions. So you can prove both directions. So for the forward direction, then it says let A be a standard matrix of linear transformation, this one, then T is 1 to 1 if A of X has trivial solutions. So let's prove forward direction. Now, let's assume that T, so we can say, assume that the transformation T of Rn to Rm is 1 to 1. So let's use the assumption that the transformation is 1 to 1. Then let the vector U be the solution of AX equals to 0. AX equals to 0. Then T of U now is equals to what? Is equals to 0. And this is equals to A of U, which is equals to A of A. Now, since T is linear transformation, then we also have T of 0 equals to 0 vector. T of 0 equals to 0 vector. Then therefore, since T is 1 to 1, then T of U equals to T of 0. T of U equals to T of 0. Therefore, this implies that U is equals to 0. This implies that. So AX equals to 0 vector has the trivial solutions on. Has the trivial solutions on. Now, in the other direction, so to prove the backward directions, so we can assume that A of X equals to 0 vector. You can use the assumption that A of X is equals to 0 vector. Has trivial solutions only. Has trivial solutions only. Now let's U and V to be the elements of Rn such that T of U equals to T of V. T of U equals to T of V. Then T of U minus V is the same as T of U minus T of V, which is equals to 0 vector, which is equals to 0 vector. Then A of U minus V is the same as also 0 vector. So therefore, then U minus V is equals to 0. That means U is equals to V. So T is 1, 2, 4. So T is 1 to 1. Okay, let's meet on. I forgot on Friday to record the class, but I posted the notes in Moodle. So I recorded this one, so I will post the class in Moodle.